Hello, and welcome back to Physics 123, Quantum Mechanics 1. We are still on the second chapter of this course, which is all about the time-independent Schrödinger equation. So let's first review what we have learned in the previous lesson. So we have derived this time-independent Schrödinger equation. So it's an equation which is purely a function of position, say x in one dimension, and it's also an eigenvalue equation. So we also have discussed about the orthonormality of the stationary states, the time-independent wave function psi, and basically they follow the orthonormality condition. And they're also normal. So they're both orthogonal. They are all mutually orthogonal and normal. And we also have defined the true wave function, the time-dependent wave function, as a linear combination of the time-independent wave functions, where the linear combination coefficients Cn's can be obtained using the Fourier's trick. And basically, these linear combination coefficients actually represent the probability of finding or the probability that a particle is in state psi n, or that the particle has an energy En. And the average energy of a particle is basically just the weighted mean of all of its energy levels. So in the previous chapter, we also have discussed the normalization of the wave function. So we will still be using this concept. So the integral of the absolute value of psi squared must be equal to 1. So it's equal to the total probability, which is equal to 1. Take note, in our previous lesson, the psi star psi, or the absolute value of psi squared, is the probability density. So for this lesson, we will be now talking about the infinite square well potential energy. So this is our first potential energy that we will be discussing, and we will try to find the wave functions if a particle is trapped in this potential, and the energy levels of a particle trapped in this potential. So in other books, they also call this type of situation or problem as the particle in a box. So let's now start the lesson. So this is what the infinite square well potential energy looks like. So this is the condition. So the potential energy is 0 inside your infinite square well from 0 to a, and infinite beyond the well. Or otherwise, when x is greater than a or x is less than 0, then infinite. So if you plot it in terms of a function, if you draw the function or sketch this potential energy function, it will look like this. So from 0 to a, the potential is 0, so u is 0. And beyond 0 and beyond a, the potential is actually infinite. So outside the well, the potential is infinite. Therefore, a particle cannot cross this border or boundary here. Meaning, if the particle cannot cross that boundary, the wave function outside the well must be 0, implying that the probability of finding the particle to the right of a, or for x is less than 0, is 0. There's no chance that you will find the particle outside the infinite square well, because this is an infinite, something like an infinite barrier. You cannot penetrate this barrier. So we will try to solve what are the states of the particle if it is trapped in an infinite square well potential energy. So you can actually think of this as a one-dimensional box. So box with one dimension. So if we think of a box, Actually, we will generalize this later to a three-dimensional, to an actual box. So we will try to find the stationary states, psi n, and the corresponding energy levels En. So we do this by solving the time-independent Schrödinger equation. So inside the well, the potential is 0. So our time-independent Schrödinger equation just simplifies to this. So take note, supposedly napanayo plus u psi there. But u is 0, so it's just simplified to this. So rearranging the terms, we get this. We let this term here, 2me over h bar squared, as our k squared. And then we get this differential equation. So actually, I have dedicated a review section in how to solve this equation. So please visit those review topics. So the solution to this are e to the I kx or e to the negative I kx, or we can also write the solution in terms of cosine and sine kx. So in order to, so basically this is just the general solution. In order to find the specific solution, we need to first establish our boundary conditions. So the first boundary condition is at the boundary. So we have two boundaries actually here. X is equal to 0 and x is equal to a. So at these points, at these boundaries, the wave function must be continuous. So whatever's the wave function inside the well, they must be continuous when they reach the boundary. But since the wave function outside the well is 0, so therefore the wave function at the boundary must also approach to 0, so that it will be continuous. So at the boundary, the wave function must also be 0. And at the boundary, the derivative of the wave function must also be continuous. So in fact, it will also be 0 because the derivative of this is 0. Okay, so we apply boundary condition 1 to our general solution of the wave function. So at x is equal to 0. So when x is equal to 0, cosine of 0 is 1, sine of 0 is 0. So at x is equal to 0, you will get this. So a plus 0 is equal to 0. So therefore, a is equal to 0. So wala na siyang term. And we are left with b sine kx. So a is equal to 0. Now, if we apply boundary condition 1 at x is equal to a, so when x is equal to a, so you have b sine ka, it must also be equal to 0. So at x is equal to a, the wave function must also vanish. It must also be equal to 0. This is the first boundary condition we're talking about. So what does this mean? B sine ka is equal to 0. Obviously, b cannot be equal to 0, because if b is equal to 0, then a and b are both 0. Your wave function is 0. So b cannot be equal to 0. So therefore, sine ka must be equal to 0. So what happens when sine theta is equal to 0? This means that theta, or in this case ka, must be equal to a multiple of pi. So ka must be equal to a multiple of pi. So pi, 2 pi, 3 pi, 4 pi. So the sines of those angles are 0. And we can now get an expression for k. K is just n pi over a. So where n is from 1, it's an integer from 1, 2, 3, and to infinity, essentially. Note that we didn't take into account n is equal to 0. Why? Because if n is equal to 0, meaning k is equal to 0. And if k is equal to 0, sine of 0 is 0. So you will again go back to the psi is equal to 0 solution. And we usually don't consider the 0 wave function because it is what we call the trivial solution. 0 is almost a solution to every equation. And we usually don't include the trivial or the obvious solution, which is 0. So we only start from 1. So our wave function is now almost very specific. It's now b sine n pi x over a. So we let k equal to n pi over a. So take note, we initially defined k squared as 2me over h bar squared. So from this result that we obtained, k squared is just n squared pi squared over a squared. So this one. So we can now solve for e. And based on this result, there are actually, e is not only one variable. Since k has many values, so take note, k depends on n, and n starts from 1 to infinity. It's an integer. So therefore, n, or the energy of the particles trapped in an infinite square well potential, or a particle in a box, one-dimensional box, also have different values due to the different values of n, which starts from 1. So if you will notice, if n is equal to 1, E1, which is pi squared h bar squared over 2ma squared, is actually what we call our ground state energy. That is the lowest energy state of the quantum particle. And E2 is the first excited state energy, E3 is the second, and so on. So if you relate this to, say, to us, in reality, the ground state for us humans, our ground state is the state wherein we consume the lowest amount of energy. And what do you think is that state? So that is the state where we are sleeping. So for us humans, the sleeping state, our sleeping state is our ground state. So essentially, you can think of a particle in the ground state as a particle that is essentially sleeping. So it uses the lowest energy possible. So please don't be confused with that. Don't think even for a second that you're not using energy when you're sleeping. In fact, you're actually using, because you're burning energy, you're using energy even when you sleep. That is why when you wake up, you feel hungry, because you lost some energy while sleeping. Okay, so in order to find this constant, or say this this constant b, this is actually a normalization constant, and we can find this by normalizing. So we use the normalization condition for the time independent wave function, so this one. So we substitute. So since these are real, so the conjugates of this are just themselves. So you get this, you use the orthogonality condition for sine. So if n prime is equal to n, or sometimes we put another dummy index here, m. Anyway, it doesn't matter. So basically, sine squared n pi x over a is basically just a over 2. So this integral is just a over 2. So therefore, b is equal to square root of 2 over a. And we now find the states of a particle trapped in an infinite square well potential energy. So take note, n here starts from 1. N doesn't start from 0. It starts from 1. Again, we don't want the psi is equal to 0 solution, the obvious or the trivial solution. So psi 1 here is what we call the ground state, and its corresponding energy is E1, the ground state energy. Psi 2 is the second excited, psi 2 is the first excited state. Its corresponding energy is E2. And then psi 3 is the second excited state, and so on. So this looks like the spherical harmonics when we discuss about harmonics in waves, where the fundamental frequency f1 is f1, and the f2 is the first harmonic. So you can think of it as like that. The excited states are the harmonics. The ground state is the fundamental frequency. Okay. So let's now try to visualize this wave function. So when n is equal to 1, that is actually the ground state, psi 1. So n is equal to 1, sine pi x over a. When n is equal to 2, so you have 2 pi x over a here. When n is equal to 3, you have 3 pi x over a. So this is our ground state, this is our first excited state, this is our second excited state. So psi 1 will look like this. So it looks symmetric with respect to the center of the well. Psi 2 the plot of psi 2 is actually like this. So it looks anti-symmetric with respect to the center of the well. And psi 3 will look like this. It actually is symmetric with respect to the center of the well. So actually, the wave functions are alternatively even and odd states. When I say even, symmetric. When I say odd, anti-symmetric. So they're even and odd states with respect to the center of the well. So of course, you will notice that these wave functions obeys the boundary condition. They die down or they go to zero at the boundaries. So continuous. This is what we mean by continuous wave function. It's not it's defined. It's not undefined at the boundary. So it's defined at the boundary. So it's since zero na ang wave function here, so therefore at the boundary it will be zero. Okay. So of course these wave functions obey the orthonormality condition and the normalization condition. And since our wave functions are in terms of sine n.pi over a, then we will use the orthogonality condition for sine. Okay, so this is in one dimension. So if you now have a two-dimensional particle trapped in a two-dimensional box with where the length of the box or dimension of the box are now a and b, so it's two dimensions. So you will have something like have square root of 2 over a and square root of 2 over b. So you will have this term, and you will have sine n pi x over a, sine l pi y over b. So in two dimensions. In three dimensions, so this is now the true particle in a box with dimensions a, b, and c. Of course, if you have a cube, this is just equal to a cube. So this corresponds to one-dimensional confinement. And in terms of actual application, this corresponds to quantum wells or quantum sheets. So this one, the two-dimensional problem is actually two-dimensional confinement. Confine the particle in two dimensions, meaning it can only move in one dimension. It only has 1 degree of freedom, and you get a quantum wire. So the particle can only move in one dimension. And if you have three-dimensional confinement, that is what we call a quantum dot. So this is the bulk particle. It has no quantum effects. So quantum effects happens when one of the starts to happen when one of the dimensions is in the quantum na realm, usually in the nanometer na width. So if you reduce the width of your, say, material to the quantum na realm, nanometers na realm, then you will get a quantum well. In a quantum well, a particle in the quantum well can still move in two dimensions. So it's just confined in one dimension. But for a quantum wire, if a particle is trapped in a quantum wire, so two of its dimensions are now confined. So meaning it only has 1 degree of freedom, can only move in one dimension, hence the term wire. And finally, if you have the particle in a three-dimensional box, it's actually a three-dimensional confinement. So the particle actually cannot move in either x, y, or z dimensions or axes. So therefore, it's literally trapped. And that's what we call a quantum dot. So when this happens, the energy of your particle becomes quantized. So when you say quantized, it's just per energy level. There's nothing, it's discrete. The energy levels are discrete and there's nothing in between the levels. Okay. So let's have an example now for a particle trapped in an infinite square well potential. So suppose you have a particle trapped in the infinite square well potential energy and they start out in this state. So this is the initial wave function, where x, of course, is from 0 to a, the width of our one-dimensional box. So what is the wave function at any time t? So unlike in the previous lesson, where the initial wave functions is in terms of the psi n, c1 psi1 plus c2 psi2, here it's not like that. We can't automatically get the wave function at any time t. So we actually want this. So we already know the psi n's, the form of psi n's. We have already solved this. It's square root of 2 over a, sine n pi of x over a. And the e n's here are given by this one. N squared pi squared h squared over 2ma squared. So the unknowns actually here, in order to solve this wave function at any time t are the CNs, the linear combination coefficients. So at time is equal to 0, so when t is equal to 0, that what? So unlike our previous example na naka-arrange na siya daan into C1 side 1 plus C2 side 2, this one is not like that, not exactly like that. So we need to use Fourier's trick in order to solve this linear combination coefficients. So, but before we do that, we first normalize our wave function. That's always the first step. So if there's a normalization constant there, you need to first get that normalization constant. So we have learned in the previous chapter that once you normalize your wave function at time is equal to 0, it remains normalized at all future times. Meaning, when you say normalize at all future times, at any time t, the total probability, the area under the curve of your probability density is always equal to 1. So always 100% probability. It's not possible that the probability will be greater than 100%. So we use the initial wave function to normalize our wave function. And doing so gave us this. So essentially, conjugate of this, since real, these are all real, there's no imaginary part here, so it's just basically the square of the initial wave function. So that one. So this will give you 3 integrals. So if you expand this is a squared minus a squared minus 2ax plus x squared multiplied by x squared. So you have 3 integrals, and those are just power integrals, so I will leave that to you. So you will actually get a is equal to square root of 30 over a to the 5th, or a to the 5. And therefore, your initial wave function, your normalized initial wave function, will look like this. So we can now proceed in finding the linear combination coefficients. Again, we know the form of our excuse me, of our stationary states, psi n, and we already know the normalized wave function. So we substitute these two to this equation here, and we get this equation. So we simplify further. This actually will become 2 integrals, x sine n pi x over a, x squared sine n pi x over a. So what will we do? What we do here is we will let u be equal to n pi x over a. So therefore, if we use that change of variable substitution, we let u is equal to n pi x over a. So therefore, x is equal to a over n pi u. So we can replace x here by a over n pi u. So there's a factor of a over n pi. And dx is a over n pi du. So there will be 2a over n pi for this integral. So a over n pi squared, u sine u du. So the limits will now be changed from 0 to n pi. Similarly, we use this change of variables from x to u, and you will get this integral. Okay. So normally, if I'm giving you an assignment, I will leave the integral formulas for you to find out. But in examples and in the actual exam, I will always be giving the integral formulas needed for each problem. So for this problem, we can use these integral formulas. So these are indefinite integrals. You still have to evaluate this at the limits. So integral of u sine u du is this one, and integral of u squared sine u du, which is the second integral here, will be given by this one. So you do that, and this integral is just equal to this, and this integral will just be equal to this one. Okay, so we finally substitute all of these results, all of these integral values, and we get this value. Further simplifying all the constants, we get this. Now, cosine n pi. this term here actually have a value of 1 or -1. So depending on the value of n. If n is even, so cosine 2 pi, cosine 4 pi, cosine 6 pi, the value is +1. And if n is odd, so cosine sa pi, cosine sa 3 pi, cosine sa 5 pi, the value of cosine n.pi for n is odd is -1. Now, if n is even, this is +1, so 1 minus 1, 0. Your CNs are 0 for n is even. And if n is odd, then this is -1, so you will have 1 minus -1. So this term will become 2 if n is even. So essentially, this term here, this whole term here is 0 if n is even, and this is +2 if n is odd. Okay, so we can then simplify our CNs to this. So this means that the CNs, the linear combination coefficients, are odd. The even linear combination coefficients are all 0. So there's only C1, C3, C5, C7, C2, C4, C6, and the other even coefficients are all 0. So we can now construct the wave function at any time t, because we already know psi n, we already know en, and we already know the CNs, the linear combination coefficients. So substituting all these results, so this is our CNs, where n is odd. This is our psi n's, and this is our ENs. So substituting that in this equation, and we will get this answer. So take note that in the summation, we only consider the odd n's, and n starts from 1. So 1, 3, 5, 7 up to infinity. Okay. So of course, at time is equal to 0, this wave function should reduce to our initial wave function. So you will notice that the summation, you just find this summation. So at time is equal to 0, you will have this summation. The summation of 1 over n cubed sine n pi x over a. And I will let you find that out for your own, that this will reduce to our initial wave function. So what if we have an additional problem for this state or system? So for instance, you are further asked, what is the probability that when you measure the energy of the particle, you will get this energy? And what is the average energy of the particle? Okay, to find the probability of a particle having energy En, or a particle being in the state psi n, so we use this equation. So clearly, if you will recall, this is our Cn's and this is our En. So clearly, this energy level is for n is equal to 1 pi squared h bar squared over 2 ma squared. So therefore, the question essentially is, what is the probability that when you measure the energy of the particle, you will get E1? So essentially, we need to find P1, which is just the absolute value of C1 squared. So since this is a real quantity, there's no imaginary here. So basically just the square of this one, for n is equal to 1. So for n is equal to 1, so you have this. And this is approximately this, or in terms of numerical form, it's 0.9985, or in terms of percentage, 99.85%. So when you measure the energy of this particle trapped in this infinite square potential with initial state, this one, there is a 99.85% chance that its energy is E1. So meaning, there's also a 99.85% chance that it is in the state psi 1, or it is in the ground state. So 99% chance nga natulog ang your particle is essentially sleeping. It's in the ground state. Now, for the second question, what is the average energy of this particle? So you already have an idea here, because 99 point round of 99.9%, there's 99.9% that the particle is in the ground state. So meaning when you solve for the average energy of the particle, it should be close to the ground state. So we use the weighted mean formula. So basically you have C1 squared E1 plus C2 squared E2. So you multiply the probability with its corresponding energy and you sum all over the energy values. So doing so will give you this. So now you have a 1 over n to the fourth. So En as a factor of n squared, and the Cn here is a factor of 1 over n cubed, but you still square that, so you have 1 over n to the 6, you have n squared, so you have 1 over n to the 4th. And this summation is actually just pi over 4 over 96. So you will get an average energy of 5 h bar squared over ma squared, which is just approximately your E1, pi squared h bar squared over 2 ma squared. So take note, pi squared over 2 is actually approximately 4.93. So it's very close to 5. So this is expected since the ground state has the highest probability in this specific example. Okay, let's have another example now. So suppose we have a particle again, but we are now given an initial wave function which is now written in terms of the stationary states, psi1 and psi2. So this problem is now easier as compared to the previous problem. So we are asked to normalize the wave function, find the wave function at any time t, and find the probability density, absolute value of psi squared. And we are asked to let pi squared h bar over 2 ma squared as our omega, angular frequency. So we are asked to find the expectation values of position and momentum, or the average values of position and momentum, and the average energy of the particle. So first problem, normalization. So it's just very easy. Okay, since our initial wave function is given as this, so we need to take the conjugate of this. So the conjugate of that equation is actually, so you have A, assuming A is real. So we will not assume first that our psi-n's are not real. So you have psi1 conjugate plus psi2 conjugate. But actually psi1 conjugate, our psi-n's are all real. There's no I in our psi-n. So essentially you can get rid of the conjugate na psi. But anyway, so we multiply this to this and you will get 4 terms. The first term is psi1 star psi1. Second term is psi2 psi2. Then the middle term psi1 psi2 psi2 psi1. So we invoke the orthonormality condition of the stationary state, the stationary wave functions, psi-n's. So meaning this is just equal to 1. This is also 1. This is 0 because m is not equal to n. 1, m is 1, n is 2. And same here, this is also 0. So doing that gives us a normalization constant value of 1 over square root of 2. Therefore, our normalized wave function is given by this one. Okay. Second question, find the wave function at any time t and the probability density. So again, to find the true wave function, which is the wave function at any time t, we use this formula, Cn psi n. So since this is an infinite square well potential energy, we already know psi-n's, we already know the Cn's, En's. So we are left to find the linear combination coefficient Cn's, which actually corresponds to the probability of finding the particle. So given this, and we are asked to let omega as pi squared h bar over 2 ma squared, so therefore our En's, our energy levels, can be reduced to n squared h bar omega. So using the at time is equal to 0, the initial wave function, which is just this one. So at t is equal to 0, this is e to the 0, 1. So it will be reduced to this. But this is our initial wave function, and we already have solved the normalized initial wave function. So from here, by comparison, it is obvious. We don't need the Fourier strict formula anymore, because it's obvious that C1 is 1 over square root of 2. C2 is also 1 over square root of 2. Then C3, C4, and the rest of the coefficients are all 0. So you don't need the Fourier strict formula if your wave function, initial wave function, is already in terms of the psi-n's, the time-independent wave functions. So this means that we will only have two terms in this summation, n is equal to 1 and n is equal to 2. So using the values of psi-n's and our EN's, the energy levels. So for n is equal to 1, h bar omega. For n is equal to 2, 4 h bar omega. So we use that, substitute those values here, and we get this equation. So this is the wave function at any time t. Now, to get the probability density, which is the absolute value of the wave function squared, so we take the conjugate of this and multiply it with this. So take note, there's now an imaginary terms here, e to negative I omega t. There's e to negative 3i omega t here. So we take that into account. So basically, the conjugate of this will have a term containing e to the positive I omega t and e to the positive 3i omega t. That's the conjugate. So you multiply that conjugate with this term and you will get this result. So again, the cosine term here is from the definition of cosine again. So cosine theta is e to the I theta plus e to the negative I theta over 2. That's our definition of the cosine theta. So our probability density here is still oscillating, and its frequency of oscillation is actually 3 times the omega, 3 times the given omega here, 3 times the natural frequency omega. So how about the expectation values? So similar with what we did in the first chapter, if you want to find the expectation value of a physical quantity, you sandwich them in between psi star and psi. So in this case, for position, since x is just a multiplication operator, so you can just use this formula, x times the probability density squared, where the probability density is this one. So you square that one. Sorry, so sorry, I forgot to put the square in the previous slide here. So there should be an absolute value squared in the previous slide. So just take note of that. So we use that, substitute that here. I will just leave this to you, the integration to you. So you use this integral formula. So again, similar with the previous problem, you let u is equal to pi x over a. So you will get integral formulas, integrals of these forms. So using those these integrals, you can get the expectation value of position. So in this case, you will notice that the expectation value of position x is also oscillating with the same angular frequency 3 omega. So the expectation value is not constant in time. Depending on the time, the expectation value or the average value will change. That is the general expectation value. It's always changing. So for the expectation value of momentum p, we do the same. We sandwich the operator form of momentum inside psi star and psi. But we can also use the other formula, m times dx dt. So mass times velocity, mass times the quantum velocity. But again, you can only use this formula if your expectation value of x depends explicitly on time, such as this one. So instead of using this integral, we just use this integral na lang, because our x here, our expectation of value of x rather, depends explicitly on time t here. So getting the derivative of this with respect to time, multiply by m, and we get this value here. So the expectation value or the average momentum is also oscillating with the same frequency 3 omega. So both position and momentum expectation values or averages are oscillating with time. So how about the average energy of the particle? So we get that by taking the expectation value of the Hamiltonian. So again, we can use this equation, or since this is a discrete case, instead of integrating, we can just use this summation, the weighted mean of the energies. So we know that there are only two terms in this summation, n is equal to 1 and n is equal to 2. And C1 is 1 over square root of 2, and C2 is 1 over square root of 2 also. So En is this one. So meaning E1 is this one and E2 is this one. So the probability of being in state psi 1, or the probability that if you measure the particle, it will be in state, if you measure the particle's energy, it will be E1, is this one. So absolute value of C1 squared. So square of this, 1/2. Similarly, it has the same value with P2. The probability of getting E2, it's also 1/2. In this summation here, so C1 squared E1 plus C2 squared E2. So basically 1/2 E1 plus E2. And the formula reduces to the ordinary average. It's just the ordinary averaging, right? You add all of the terms, divide by the number of terms. So in this case, you add all the energies divided by the number of energies. So in this case, E1 plus E2 divided by 2. So the regular average. So the expectation value, the quantum average, essentially just becomes the regular or the classical average. So it's 5 pi squared h bar squared over 4 ma squared, or in terms of the omega that we are left to define earlier, it's 5/2 h bar omega. So that's the end of the first that's the end of this lesson, which is on a quantum particle trapped in an infinite square well potential, or particle in a one-dimensional box. So for the next lesson, we will be discussing about a particle trapped in a harmonic oscillator potential. So I will see you again next